we're going to look at amide hydrolysis in basic solution, which is analogous to the saponification reaction, which is ester hydrolysis in base solution. So again, you would need to have an amide. And you would have it in base. So the cation doesn't matter. In this case I'm using sodium hydroxide, but you can have different cations. But the point is there's a hydroxide, and it is going to act as a nucleophile toward the carbonyl carbon. So we'll add, and you will break the pi bond to make a negatively charged tetrahedral intermediate. Now, right now, if you were to do things like we did with saponification and reform the pi bond, the best leaving group you would have is the hydroxide. So we need to make a better leaving group. And this can be done because you are in water. So we're going to use water as a way to get a proton. And you can give this proton to a couple of different places. The more negative position is most likely to pick it up. So right now, use your negatively charged oxygen to pick up the proton and give electrons back. This will be equivalent acid-base chemistry, because right now what you have is the conjugate base of an alkoxide, and you're going to make a hydroxide which is equivalent base strength. So that's acceptable to do, and by doing so you will make a neutral tetrahedral intermediate. At this point, you need to react with another molecule of water. And the water is going to act as a proton source, because you're not going to get a proton from a hydroxide. And you can put this proton on either of the oxygens or on the nitrogen, but the step that is productive is to give it to the nitrogen, otherwise you're going to have to take it right back off again. So make sure it's the nitrogen that comes in here and takes the proton from the water and gives the electrons back. So you got a lot of OH minuses in there. Now you've got two of them to balance all the charges. So at this point you do have a good leaving group in ammonia. One of these OH groups will come in and it will remove a proton from one of the OH groups attached to the tetrahedral intermediate. So we'll take it off here. As that is occurring, this OH bond breaks, and it will use that pair of electrons to make the carbon-oxygen double bond. At the same time, the carbon-nitrogen bond breaks. So that you regenerate water. You still have a hydroxide left over. And we now have our carboxylic acid. And ammonia. Now you have an acid in the basic solution, so this hydroxide that you still have left over, it is going to come in here and remove the proton, give electrons back to the oxygen, so that now you've created overall two waters. Carboxylate, which is a much weaker base and is the driving force for this particular reaction. Okay, and you also have an ammonia. Now this is where it will stay. It has nowhere else to go. It's irreversible because you've made a much weaker base. Now if you wanted to after it's had time to run through, you could protonate this carboxylate with an acid source, but you'd have to add that after the fact. It would not be there initially. You could add after and generate the carboxylic acid, but it doesn't just stay as a carboxylic acid. You would actually have to add acid back in.